Welcome to a lecture series on advanced linear algebra. Today we will discuss about linear transformations. So far we have learned what is vector space and how to compute the different subspaces, concept of basis, dimensions. Now we want to extend this concept by introducing mapping between two vector spaces. Introducing a terminology linear transformations. Actually, most of the part of this course will depends on these functions. So it is very important. Let me define first what is linear transformations. Linear transformation. Consider V and W be two vector spaces over a field, say capital F. A mapping T or a function T from V into W is said to be a linear transformation from V into W provided for any alpha and beta belongs to V and C belongs to capital F. T of C alpha plus beta equal to C times T of alpha plus T of beta. So this is the definition of a linear transformation from a vector space V into W. See, here we have capital V and capital W. Both the spaces have their individual vector additions, scalar multiplications. So, here C alpha plus beta, C times alpha, this scalar multiplication is scalar multiplication in capital V, and this plus vector addition is a vector addition in capital V. Whereas in the right hand side, where you have written C again times C or T of alpha, this C times means this is scalar multiplication in W, and this addition, that C T alpha plus T beta, this plus is basically vector addition in W please. So, let me take some examples. Consider the identity mapping, identity function I from vector space V to V. So, it is mapping alpha goes to alpha. So, this means that I of C alpha plus beta will be equal to C alpha plus beta. So, this is equal to, I can say, C times I of alpha plus I of beta. So, I is a linear transformations, linear transformation. Now onwards I will write LT from V into V. Let me take another examples. Consider A is an M cross N matrix over capital F, that is my field, maybe real number, maybe complex number, some field capital F. Then consider a function t of some capital X equal to something like Ax. So, I am defining function t, t is basically function from f n cross 1 to f m cross 1. So, I have considered function t from f n cross 1 to f m cross 1 defined by t x equal to x. Okay. Claim t is a linear transformation from f n cross 1 to f m cross 1. So, my vector space capital V is equal to f n cross 1, whereas capital W is f of m cross 1 please. Proof is very straightforward. For any x 1 and x 2 where say x 1 is equal to, let me consider x 1 x 2 prime x n prime and x 2 is equal to x 1 double prime x 2 double prime x n double prime transpose, and for C belongs to capital F. Now, C times x 1 plus x 2, this is equal to C x 1 prime plus x 1 double prime and C x n prime plus x n double prime transpose. So, T operating on C x 1 plus x 2, which is equal to A times your C x 1 plus x 2. According to definitions, this is my definition star, suppose star. So, I am getting this is equal to this quantity. Then if I use this even matrix multiplication also, this is C is a constant is equal to C times A of x 1 plus A of x 2. This is equal to C times T of x 1 plus T of x 2. So, T is a linear transformation from f n cross 1 to f m cross 1. Let me take another examples. Consider V be the space of all real valued continuous functions defined from R real line to R, then define the map say T on V as below. T f of x I am defining as 0 to x f of t dt. We know this space is not a finite dimensional space, although it is a vector space. Okay, so, I have taken a function t from vector space V to V defined by t of f basically equal to 0 to x f t dt. Claim T is a linear transformation from V into V. Certainly the right hand side of this expression, suppose this is I am giving it a double star, it is again if and real valued continuous function. So, it will be again in capital V. So, the way it has been defined, so I can say T is a mapping from V to V. Now, we have to prove that it is a linear transformation. For any F1 and F2 belongs to capital V and C belongs to capital F, we have say H is equal to C F1 plus F2, then TH of x, this is equal to 0 to x C F1 plus F2 ds type. So, I can write like this. So, this is equal to, since integration is a linear, so I can write down is equal to C times 0 to x F1x ds plus 0 to x F2s ds. So, T is also a linear transformation from V to V itself please. Consider T is a linear transformation from V into W. We have for 0 belongs to V, 0 is a 0 element of V, T of 0 can be written as T of 0 plus 0. So, this is equal to T of 0 plus T of 0. So, this implies T of 0 equal to 0, that is 0, that is 0 element of W. Note that 0 element of V is not necessary to be 0 element of W. For examples, say T is a map from F3 to F3 cross 1 to F2 cross 1 defined by say x goes to say 1 2 minus 1 minus 1 0 1 this into x1 x2 x3. So, if I consider these ones, then I see that 0 element of F3 cross 1 is 0 0 0 transpose, whereas 0 element of F2 cross 1 is 0 0 transpose. So, we see that, but 0 element of V goes to 0 element of W. This is a property of this linear transformation case. So, I can say the property of linear transformations. This is second property, I can say like this, for alpha 1, alpha 2, say alpha k belongs to V and C1, C2, Ck belongs to capital F, where I assume that V and W both are defined over the field capital F. Okay. Then we see C1 alpha 1 plus C2 alpha 2 plus Ck alpha k belongs to V and T of C1 alpha 1 plus C2 alpha 2 plus Ck alpha k can be written as C1 T of alpha 1 plus C2 of alpha 2 plus Ck T of alpha k. So, this is because of the definition that T of C alpha plus beta is equal to C times T of alpha plus T beta. In summation form, I can say like this: C I T of alpha I equal to 1 to k. So, one can write like this also. So, now I will introduce some more terminology. Range space of a linear transformation. What is that? Let T be a linear transformation from V into W. Then the range space of T is defined as collection of all small w belongs to capital W such that for each small w there exists V belongs to capital V, T of V equal to W. Okay. That is mathematically, if I write range space, if I denote RT, RT equal to connection of the all small w belongs to capital W, so that for each such w there exists small v belongs to capital V and T of V equal to W. That is RT is equal to, I can set up all the TV which is belongs to W. Both are same place. I mean collection of the all the image elements of the elements of capital V. RT is subset of W, but RT is also a subspace of vector space W. How? Because for any W1 and W2 belongs to RT and C belongs to capital F, we have there exists V1 and V2 belongs to capital V with T of V1 equal to W1 and T of V2 equal to W2. So, now C times W1 plus W2 equal to, I can write down C times T of V1 plus T of V2. So, this is equal to, I can write down from the definition of the linear transformation T of C V1 plus V2, this one which belongs to my RT. So, RT is also a subspace of vector space W. Let me introduce one more terminology. The dimension of RT is called as dimension of range space of T, which is called as rank of T. Another terminology let me introduce, this is called null space. Null space of T. The null space of T, which I am denoting as NT, is defined as set of all the V belongs to capital V such that T of V equal to 0 element of W. This is called the null space of T. So, certainly NT is a subset of capital V. NT is also a subspace of capital V. So, RT is a subspace of W, whereas NT is a subspace of capital V. Dimension of NT is called as nullity of T. So, before proceeding more about these two subspaces and whether any possible relation is there or not, let me prove one nice results, that is these theorems, that is existence of linear transformation please. Let V be a finite dimensional vector space over capital F, and B equal to alpha 1, alpha 2, alpha n be an order basis. Order basis of V. Let W be a vector space over capital F. Let beta 1, beta 2 and beta n be any n elements of W. Then there exists a linear transformation T from V into W such that T of alpha I equal to beta I for I equal to 1 to n, and it is also unique, and T is also unique. So, this is a very important results. So, the proof is not difficult, but most of the time students used to forget this issue and face lot of difficulties to solve the problem please. So, this existence of linear transform is very important results in the linear algebra also. Here we see we have mentioned about the dimension of V as a finite. We have not mentioned about the dimension of W, nothing. We have mentioned alpha 1, alpha 2, alpha n are the linearly independent elements of V, whereas beta 1, beta 2, beta n, there are any arbitrary elements of W. We have not mentioned anything whether they are linearly independent, dependent, nothing. So, the beauty of this results that for any order basis B on capital B, if one give n elements of W, one can have a unique linear transformations from V to W such that T of alpha I equal to beta I. Let me quickly sketch the proof please. Consider alpha belongs to V be any element. Since alpha belongs to V, alpha can be written as a basis element of V. So, there exists C1, C2, some n scalar Cn belongs to capital F such that your alpha is equal to C1 alpha 1 plus C2 alpha 2 plus Cn alpha n. Now, define a function say t from V into W as below. When T of alpha I am defining as, of course, this is equal to, I can write down as sigma Ci alpha I equal to 1 to n. Okay, T of alpha I am defining as C1 beta 1 plus C2 beta 2 plus Cn beta n. So, I am defining, this is my definition of the functions. Claim T is a linear transformation from V into W. See, it is a function from V into W, that is clear, because beta 1, beta 2, beta n, there are elements of W, and taking the linear combination of beta 1, beta 2, beta n, that will be certainly will be in the W place. So, it is a function from V to W is clear, and is also well defined rule place. So, this implies also I can say T of alpha I equal to beta I. I have also considered these things. Consider gamma belongs to V be some other element, and gamma equal to, again I can write down as a di and alpha I equal to 1 to n, because B is an order basis for the space V. So, and gamma belongs to your V. So, gamma can be written as like this thing is. So, according to the definitions, T of gamma will be sigma di and beta I equal to 1 to n. Now, you see what is C alpha plus gamma? This is equal to C times sigma, okay, Ci alpha I plus sigma of di alpha I. So, this is equal to, I can write down sigma C into Ci plus di into alpha I. Okay. So, C alpha plus gamma equal to like this thing. So, T of C alpha plus gamma according to the definition will be equal to C into Ci plus di into beta I. Again, C times T alpha plus T gamma will be equal to how much? According to the definition we have seen C times sigma C I beta I plus sigma d I beta I. So, this is equal to sigma C times C I plus d I times beta I, which is equal to T of C alpha plus gamma. So, T is a linear transformations. Now, claiming it is unique. Suppose not. Let U is another linear transformation, which is from U is mapping from V to W such that U of alpha I equal to beta I. Then U of alpha will be equal to U of sigma C I alpha I equal to 1 to n, which is equal to sigma C I U of alpha I equal to sigma C I beta I, and this is nothing, is basically your T of alpha. So, this implies U equal to T. So, we see that there exists a unique linear transformation from V into W. So, we see that for a given vector space V of finite dimensional space, and when the order basis is given to it, suppose n elements, if it is given from the other space W, then there exists a linear transformation which is also unique from V to W such that above relation, that T of alpha I equal to beta I, this relation holds good. Thank you.